So what exactly is redox chemistry? Well, redox chemistry is going to be for us a different way of looking at reactions. And if you think back to where we've had before, where we had different types of reactions, we had reactions based on synthesis and decomposition, how the atoms are being rearranged. We had reactions where it was about the, say, a combustion reaction, about the reactants. We had neutralization reactions about the reactants, and redox is going to be a little bit different again. But what I want you to do before we dive into thinking about what redox is to look at some reactions. Now, you don't need to write these down. If you want to, you can, but you don't really need to. But if we take a look at some reactions that we're familiar with and try and figure out what they have in common. Well, the top one you could say is a synthesis reaction, and the middle one is a single displacement, the bottom one is a decomposition. So they're certainly not the same kind of reaction, but they do have something in common. And you can probably guess they're all types of redox reactions. Well, the other type of reaction we had, or one of the other types I should say, is this bottom one, and that's a double displacement. And it's different. It's not a redox reaction. Well, what's a redox reaction? The first three, as I mentioned, were redox reactions, and the word reduction, you don't need to know this, you don't need to know the history, but it's worthwhile to understand why we use the word reduction. Well, it comes from metallurgy, where if you took an ore in it, you reduce it to the metal. Now, if you think about the reaction, if you were to take iron ore and react with carbon, you would get iron. So you would take an ore and you would reduce it down to its parts, iron and some other part. Or if you thought about it in terms of mass, the mass of that stuff would be reduced. And oxidation comes out of, well, you can probably guess, reactions with oxygen, where we started to understand it in a certain way, and then we expanded our knowledge. Well, what does it mean now? And then just an oxidation reaction. And what we looked at there, if you look at that second one, again, not something we need to write down, is that second reaction is kind of similar, but it's not involving oxygen. So that's kind of what I mean by our understanding expanded. Finally, we get to a redox. A redox reaction is a reaction that involves a change in the oxidation state of some of the atoms. It doesn't have to be all of the atoms, but some of the atoms. So now we need to know what an oxidation state is. Oxidation state is going to be similar to an ionic charge, and if you look at those reactions previously, in most cases we could work with ionic charge. What was the charge in iron before? What was the charge in iron after? So here's one of those reactions again, and we would look at this when we say that sodium starts out as no charge because it's a neutral atom, and it finishes up in a compound. We know from grade 11, sodium, probably grade 10, sodium is always +1 in compounds. And we could say a similar thing for chlorine in that it goes from a 0 neutral charge to a -1. And that's what I mean by a change in oxidation state. Well, oxidation state is more than just ionic charge, but it's going to be kind of related. And now we're going to get a better idea of what's going on. So, reduction. We learned the origin from metallurgy. It doesn't apply anymore. Reduction is going to be the gain of electrons. Now, if you're thinking that that makes no sense, that I'm gaining something, I'm calling it reduction, part of that is the history, but we can actually make use of the word reduction as well. Oxidation number is going to go down. It's going to be reduced. It's going to get more negative. So, for example, that chlorine a moment ago was going from a 0 to a -1. It was being reduced, and does that by gaining electrons. Oxidation, on the other hand, is the loss of electrons. And so sodium lost electrons, went from 0 to +1, loss of electrons, and then the oxidation number goes up, or it gets more positive. Now, what might be helpful is to think of charges as a number line. So obviously we can go higher than +3, just put a few on here. Oxidation is any time where that thing is moving in the positive direction. So even if I went from a -3 to a -2, that's loss of electrons. It's an oxidation. It doesn't have to be going from a 0 to a plus. It doesn't have to be going from whatever. But as long as it's moving in that toward the positive direction. And likewise, reduction is anything moving in a getting smaller each time. So even going from -2 to -3, that would be a reduction. Well, how do we get the oxidation numbers? We said it's similar to the ionic charge, but it's not always going to be ionic charge. But if we took any compound and treated it, we're not changing our understanding of ionic bonds or covalent bonds. We're not going to say everything is ionic, but if it were, and the electrons were going to go to the more electronegative element as they do in an ionic bond, what would the charge be? So again, this is not something we're changing the bonds, we're not doing anything like that. This is just an electron bookkeeping kind of thing where we say if we had to split the electrons and if it wasn't a share, what would happen? Well, the electrons would go to this atom. Okay, so we'll work out oxidation numbers that way. So there's some patterns that are useful to give us a starting point. And one of them is that any unreacted element is a neutral charge, and that means its oxidation number will be 0. And I've got a couple of examples there. I've got 3 actually. You don't need to write them all down. If you don't want to write any of them, that's fine too. A monoatomic ion. So what we had earlier was sodium or a chlorine. Any kind of monoatomic, so none of the polyatomic ions, whatever the charge state is. So the oxidation state for aluminum here is +3, and the oxidation state for bromine is -1. Hydrogen in most compounds, and for us it's pretty much hydrogen in all of our things, it's going to be +1. So water, hydrogen chloride, we're going to treat hydrogen as if it were +1. Now there's rare exceptions, we're probably never going to run into that, so if you want to leave that out, that's probably not going to cause a problem. Rare exceptions is when hydrogen does behave as a negative bonding partner. If it's with a metal, hardly ever going to run into that. Oxygen in most compounds is going to be -2. Now we actually know that from grade 11 nomenclature, right? Well, oxygen was always -2 in compounds, -2 with metals. Now we're going to treat it as always -2 in compounds, with the exception of a peroxide, hydrogen peroxide, H2O2, as an example. And just to give you a quick little scribble out for hydrogen peroxide, a peroxide is this bond here. That shouldn't be a happy face, but that's kind of what it looks like, doesn't it? But because this is a shared bond between two things of equal electronegativity, that one doesn't really count. Again, we're not really going to run into peroxides. So if you left that last line off, no problem. Well, let's use it. So here's an example of a compound. We know that the overall compound here is neutral. There's no charge, there's no ion written on there. So whatever the things add up to, they're going to have to give us a total of 0. That's going to be our net ionic charge, or the sum of the oxidation numbers. So what we do is we take what we know. So I don't know what carbon is, that's the one I'm trying to find out. So I'm going to label it as an X. Hydrogen, well, it's not one of the exceptions, so it's going to be +1. There's 4 of them in total, giving me a total of -4. Oxygen, not one of the exceptions, so it's -2. Now I have to add all this stuff up, as I mentioned, to a 0 or an overall neutral charge. Total negative equals total positive. We did that with grade 11 nomenclature with ionic bonds, and because we're now pretending that, well, if everything were ionic, so that rule applies. Working it out, we end up saying that X is equal to -2, or the oxidation state of carbon is -2. Now, quick little by the way, this table you might find really helpful, but you don't have to use it each time. If you want to have a little scribble over here, so this is going to be +1, and this one's -2, and that's a total +3, and this is, well, who knows, and it has to add up to 0. If you want to do it like that, that's fine, but I do find the table is a really good place to start. What about an ion, where the total positive charge and total negative charge aren't the same? Well, here they're not. It ends up being that the total negative charge is 2 more than the total positive charge. Well, we're going to keep track of that too. And we're going to do the same thing. Chromium, I don't really know. Oxygen is -2 in all things, and there's 4 of them, total -8. And whatever ends up, however they add up, they have to total to a -2 overall. Well, that means that the chromium, that X, is going to be a +6. Well, what if there were 2 chromiums or 2 carbons, or do the same thing? All right, then it would be, say a 2X instead of just an X. Now, this one doesn't have that, so I don't have to worry about it. A couple more important terms. We know about oxidation, loss of electrons. We know about reduction, gain of electrons. So you already have these 2 terms. The only thing I've added now is this little, what is it, an acronym? Loss of electrons is oxidation. Gain of electrons is reduction. If that helps you keep track, Leo or Gur, Your textbook, I think, says Leo says Gur, or Leo the lion, or I've known people talk about Leo was German. If that helps, great. If a little story helps you keep track of things, fantastic. If not, you still need to know that loss of electrons is oxidation, the gain of electrons is reduction. But here's where things get a little bit confusing. We can have an oxidizing agent, and the agent is the thing that causes. So an oxidizing agent causes oxidation. Well, oxidation is the loss of electrons. So if the agent causes the loss of electrons, it takes the electrons. Now, if you think about it, if something is taking electrons, what's happening to it? It is being reduced. It's gaining electrons. Likewise, the reducing agent causes reduction. It causes the gain of electrons. Well, it does that by giving away electrons. Anything that gives away electrons, it itself has been oxidized. So you have a reducing agent getting oxidized, and you have an oxidizing agent being reduced. But it all comes down to the fact that it's causing the other thing to happen. Once you get used to it, it's actually not that hard, but it does seem a little strange at the beginning. All right, so initially, that's all there is to it. Some terms, some working out oxidation numbers for a thing, and recognizing whether or not something is an a redox reaction or not. And those are the things that we're going to start with. And then we'll work with this in class. We'll get really good and comfortable with coming up with oxidation numbers and all the rest. And then we'll move on to something in the next little bit. Talk to you in class.